the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you back to episode number 74, where today we are going to be talking about rotational motion. The movements of rotation. No, that didn't make any sense, but you know what we mean. So I think this is an episode long time coming. We did mention it in a previous episode that we were going to do a rotational motion episode, and here it is. Very excited about this one.
This is pretty important, you know what I mean? When you learn about classical mechanics, you got to learn about the translational equations, and then you also need to learn about the angular motion equations, because it is the only two ways, right, of like moving.
Translational and angular.
Translational.
Yeah.
I don't know if there's another one. I don't think so. But
No. How?
anyways, so when you move, when you're moving in a rotational fashion, there's an axis, a point about which you are rotating, and the thing that moves, well, if you're looking at just like a simple case, you know what I mean? The thing that moves or changes is the angle. You know, usually we look at the angle from the positive x-axis if you're like moving in a circle on the graph. And yeah, that's the thing that moves. But of course you can get some like cool parametrizations where the distance from the rotation, the axis of the point of rotation, I guess, also changes. And I guess we can talk about that later, because that does have to do with like multivariable kind of deal, you know what I mean? Like parametrizations, that's multivariable, right?
Yeah, I mean, yeah, for sure. That would be a little, we could get into that kind of, maybe we want to stick a little to the physics today. I don't know. Yeah. Because we have been doing a lot of math episodes, which I love, but I also love physics. You know, I love that physics. So I think, yeah, I mean, we can definitely touch on those, but maybe focus a little more on the motion aspect of it, right? So one thing before we even start, I just wanted to mention the importance of this particular subject, right? Like, why do we care that something, or like the fact that something is rotating or like translating, like why is it even important? I don't know. So I'm doing this thing on the side right now with a professor. It may come up in the future of the podcast, but it's where we're basically analyzing equations of motion. And in this particular project, I realize how important it is to analyze said motion, right? Because given a scenario, given a system that's doing something, or if you're observing a particular system and you're letting it, you leave it alone and just something is happening, and you want to be able to quantify that system, you want to be able to deduce elements and properties of that system. And how do you do that? And again, this is all just to say all of this is really beautiful, and including rotational motion in this system of equations is incredibly important, because again, that's a way that it's moving, right? So an object can be completely stationary in space, but just be rotating along its own axis, right? Which is it's still moving technically. So there are just so many ways to think about it. And I just wanted to stress the importance of like everything we're going to do today is it's just kind of like translating between, pun intended, translational motion and rotational motion. And that's basically just understanding that relationship, right? And honing in on that relationship, again, will just get us to a better understanding of the properties of these rotating bodies, right? Whole point of this thing in the first place.
Yeah, so when we talk about translational motion, we have like frames, you know what I mean? I think the equivalent to a frame in rotational terms is the actual axis of rotation, because you can have like an object rotate around a certain point, and you can have at the same time that entire that point of reference is also rotating around another point of reference. So it all depends on which rotational axis. I keep forgetting like which word to actually use.
Yeah.
But do we call it the axis of rotation, the point of rotation?
Because axis would be if it's spanning something, right? Like it's a line. That like a point would be if it's a. But in this case, if it's a 2-dimensional thing, like if it's just a circle, then technically you can't say axis, right? Because you're just drawing a line through it and it's just rotating along that axis. So I guess axis would be valid. I think both would be. Even point of rotation would be valid, to be honest.
Yeah, sure.
Yeah.
So
anyways, yeah.
Yeah, I think that's all I want to say. Like
before.
Before we actually, we didn't even do the.
Yeah, that's exactly what I'm saying. So let's get that done first. News.
Okay.
Let's do it. So we are sitting at, I believe last time, again, we keep forgetting. Also, I should mention, that might be why our numbers are different. So this episode is actually being recorded. We usually do it every Saturday. This is being recorded on a Thursday because I'm not here this weekend. So that's why our numbers are different. I've been wondering, like, it's a lot lower than what we usually report, like week on week. But anyways, we'll still continue. So on Thursday, we have our followers on Spotify sitting at 3. So a quick, 300 followers that happened like in the last few days? That was pretty cool.
I guess.
Right? Because we just touched 12,000 last Saturday. And Google Podcast, I believe we're also, Parker can maybe run that number. What's the number on Google Podcasts?
Right now it's 2,064.
Still impressive. Thank you for everyone who listens over there. And
Thank you
downloads,
to
total downloads sitting up at 191,000. And
let's go.
Finally, for the last piece of information, the YouTube subscriber count. Pretty impressive, actually. Sitting at 1.2 or 1210 subscribers. So thank you for everyone who, follows on everywhere you do. Wherever you are right now, just go ahead, click that follow button. Why not? If it's on YouTube, smash that like button,
And thank
for
you so
the
much to
algo.
everybody who's been downloading the podcast. Now, make sure to leave a comment under this YouTube video to be the comment of the week.
Mm-hmm.
Actually, you can comment anywhere pretty much. We take emails.
We say the YouTube video when we're talking, but like to be honest, if it's a nice enough comment, like we'll just pick it, from anywhere. Like it doesn't really matter.
So this week's comment actually comes from an email from Abraham.
Oh.
He is studying engineering physics in Colombia, and he says he's been listening to our podcast and he thinks they're awesome. Thank you so much for your email, and we encourage everybody to let us know if they enjoy the podcast or if they have any suggestions for topics for us to talk about. I guess, we pretty much talk about anything. So if there's anything you saw on YouTube or wherever in class, let us know and we'll make an episode on it. Yep. Anything else, Ray?
Nope. I think that's it for the news, right? No more updates that we have, I think. Yeah, I think we can get into it. Let's get into rotational motion. So, we already kind of touched on, a little bit. Parker already kind of described the whole angle thing, and from the x-axis is what we usually do and whatnot. Again, that's only in 2D, but we can continue from there. But before we really get into rotational, let's distinguish between what we're already familiar with, and that's translational motion. Translational motion is something that we already know. Take a box on a plane, and you're pushing the box, right? How much ever it moved is the distance. And that motion is called translation, is the point that I'm trying to make, right? Why? Because that box or whatever object that you are moving is, with respect to the surroundings, staying the same. Like nothing is really changing, right?
And we're going to talk about like simple translations, so just like one-dimensional motion.
This is okay. Yes. The thing that I'm going through right now is simple. Is one-dimensional, right? We're just pushing a box along a plane. But even if you generalize this particular example, I think I don't really need to know if we really have to go that deep into what the difference is between something rotating and I think it's pretty intuitive. Like you can imagine something rotating, right? So that's basically the difference. And translational is what we're mainly used to and what we deal with when doing everything. So all of our equations of motion with acceleration, velocity, the big five kinematic equations, the dynamic equations, all of them are translational equations because they're all based on the fact that the object itself is not rotating. Now, if it's rotating, we add things in the mixture, right, which is a little different.
So, yeah, when you have an object that moves along a line, you have like two things at first. You have the distance and the time it took to travel that distance. And if we're just assuming like a constant velocity, then in order to calculate that velocity, you can do, distance divided by the time it took. Or if you want to know the instantaneous velocity, you take the derivative of the distance or the position with respect to time. And essentially, you start with position and you take the derivative and you get to velocity. And this is translational velocity. In terms of rotation, it's a little bit, it's not like trickier, but there are kind of two things that you can look at. Because the first thing that you can look at is the rate at which the object is rotating around your point. And so first off, you have the angular position, and what you can do is take the angle divided by the time it took to travel across that angle, and then you get the angular or the average angular velocity. And if you want to know the instantaneous angular velocity, you take the derivative of the angular position with respect to time. But there is also another thing. Oh, you can go ahead.
I just wanted to say one thing about the angular position thing, right? Like a lot of people, they're sometimes like, you don't really have a protractor just measuring the angle. Now, for those of you that remember our trig episode, which is, I believe, where we spoke about the radian, becomes incredibly important when talking about angular rotation, angular motion, sorry. So angular position, not really, again, measured with a protractor. It's mainly measured with, again, those that remember the definition of a radian or how to really measure it based on this and not a degree is very simple. So remember the whole point of rotating is that you can basically make your arc into a whole circle, right? I don't know if I explained that very well, but like wherever you are, if you are rotating, that means if you are experiencing rotating or like rotational motion, right? Then what that means your path is describing a smaller set of a circle. Like it can basically be traced out to a circle, right? The whole point to basically say, to measure the angle that you traverse, the angular position, you take the distance that you traveled, which is along the arc length, like we call it, and you divide it by the radius of this imaginary circle that you draw around this arc that you are traveling. Now, again, if you visualize that, you perfectly understood it. If you didn't, I don't know how good that was. But it's basically the angular position is simply a ratio of the distance that you travel on the circle to the radius of said circle, right? And it's equal to 1, that means 1 radian, when you exactly travel, hence the name, 1 radius equal of the circle, right? So when the arc length and the radius are equal, that means you travel the same radius, you basically travel 1 radian. And the reason it's so much easier is because now this is based off, so there's no, like it can be generalized for every case. And the best part about the radian, if you noticed, is that it is unitless. And again, we mentioned this in the trig episode, so everyone may be like having flashbacks to that one right now if you've already watched that, but the radian is unitless, and that provides a lot of advantages that we will talk about later. Yeah, sorry, you can continue, Parker.
So one thing that I always forget is the equation to go from like distance to angle. You know what I mean? And so I don't know if anybody also has this issue. Oh wait, my mic.
Yeah. Give it a sec.
Hello. Damn. Why does it even do this, man? Oh, there we're back. Okay.
Hey.
So I don't know if anybody else also has this issue, but like recently, I think like this year, I thought of an easy way to remember. So everybody knows the equation of circumference equals 2 pi r, right? There's no way you don't know that. But
that's pretty diss to some people that may not know that. No. I don't know, because there may be, I don't know. Anyway, if you don't know that, it's okay. But
now
yeah.
you know. 2 pi r.
Now you know.
Get used to it, I guess.
Yeah.
But as we know, the circumference is the distance that you travel around a circle. And that's equal to 2 pi radians, right? So the angle, and times r, the radius. Mm-hmm. So there's your equation. The distance is equal to the angle times the radius. And then, as I said earlier about taking derivatives, if you take the time derivative of both sides of these equations, the time derivative of the distance is the velocity, and this is the translational velocity, the instantaneous one. Mm-hmm. And you take the time derivative of the right side, the radius is just a constant in this case. And so you get the derivative of the angle, which is the angular velocity. And there you have your equation off the bat. Mm-hmm. that goes from translational to angular velocity, v equals omega r. Mm-hmm. And you just do the exact same thing for acceleration. Boom.
Yeah, you can further move that onto also two forms of acceleration, the tangential and then the radial acceleration, right? And similar again with that whole, I don't know if I think it was kind of explained. One, the 360 degrees, like the whole circle, is basically 2 pi radians, which is basically the kind of the deduction where we made the 2 pi r thing from, which is how it comes from, which is actually pretty cool. I know I guess we didn't really think about it before we really understood truly radians and stuff, but now that we made that connection, it's pretty cool. But yeah, continuing on to acceleration, if you want to find the angular acceleration, you just go ahead and take the time derivative again of both those sides, and then you get your alpha, which will be your angular acceleration, similar to angular velocity is your angular. So it's so angular velocity is radians per second. This would be radians per square second, right? Or radians per second squared. So the whole idea is you're just comparing your regular translational variables to your now rotational variables. And the whole point of comparing these two and saying, okay, well, what's the relationship between v and omega is also like the classic the tangential velocity is like, hey, if I cut a ball on a string, what would be its speed? You know what I mean? Like, if the sun just disappeared right now, how fast would the earth be moving? Like those kind of questions would be answered by the tangential velocity. But if you ask, hey, how fast is the earth moving right now? Well, that would be a question for angular velocity because we're moving in a circle, sort of circle, right? So it's just, again, a relationship between these variables and just continuing it down the road, right? That's basically v, omega, and stuff. And for converting it between, for the big five, what people are generally used to, the big five kinematic equations, you know, all the equations of motion, you basically just swap them. You just switcheroo. So the distance, the position or the change in position becomes the change in angle. The velocity becomes the angular velocity. And the acceleration becomes the angular acceleration, and everything else stays the same. Mm. Yeah, so everything else is time. But so everything works just by switching around these variables, which I just think is beautiful. Mm-hmm. You know?
Yeah. Also, I don't think it really made sense what you said about the Earth, because if you ask somebody how fast the Earth is moving, they're not going to give you
I guess that's valid. Velocity. No one's really giving a rating for a second. No one's really giving. But what I wanted to say is that would be the best way to quantify it, even though that is not exactly what people would say. I totally get what you mean. You would still answer the tangential velocity, but what it's actually going through is in fact rotational, is what I was trying to say.
Yeah. We are currently moving at 0.0001 radians per
yeah,
second.
we'd be moving pretty slow in terms of radians.
Yeah, so now, of course, because we love physics, we have to talk about Newton, right? So you're probably wondering, okay, when you're moving in a straight line, you can experience forces and all these things. Okay, perfect. Well, as we just described, there is such a thing as angular acceleration. And if you remember from a previous episode, which I don't exactly remember which episode it was, we talked about inertial terms.
Oh, Newton's,
which I think,
Newton's laws.
Yeah,
100%.
probably.
Where else would we have talked about it?
I don't know. But we talked about inertial terms. And when it comes to rotation, it's not as easy as just saying the mass. It is that easy when you're dealing with, one-dimensional motion, just moving in a straight line, because the mass, all the particles in that mass will be moving in the same direction. They'll have the same vector velocity vector. I don't know why I said that twice, but everything is going to move at the same time, at the same rate, in the same direction, all that stuff. And so all you're really concerned about is the center of mass. You pretend as if everything was, like, the entire mass of the body was concentrated in one spot at the center of mass, and it had the mass of the body. Boom. That's all you need. But rotation is a little bit more complicated, because you have situations where I can rotate my body around an axis that is centered in my body. Like, I can rotate around my spinal cord, you know what I mean? Mm-hmm. And if you look at every single particle in my body, some particles are going to be moving faster than others, which means that you can't consider every single particle to be identical in this case. And so, as you probably guessed, the inertial term actually depends on the actual axis of rotation and the distribution of mass. Mm-hmm. So, for example, if I'm rotating around an axis on my spinal cord, just like spinning around, I'm going to have a different moment of inertia than if I was rotating around the sun. You know what I mean? So I guess we can talk a little bit more in depth about that when we get to energy and then like torque and things like that. Mm-hmm. Which, yeah, torque is I alpha. So it translates directly to like from the Newton's equations.
Mm-hmm. So I is very, I comes in very many places, including like when we're calculating for energy and stuff like that as well, right? Like, again, translating between the translational and the rotational terms, I is, again, okay, I don't fully remember if you said this, but I is basically the rotational version of mass, right? So in your half mv squared for your kinetic energy formula, if you're trying to calculate the kinetic energy for any moving body, you just switch it up. It's half I omega squared, where I is basically your moment of inertia, which is now representing your mass, and omega, which is your rotational velocity. So again, it's a very easy switch to just get these through. Again, showing you that physics works.
I don't know if I remember this exactly.
What? Okay.
But so the moment, okay, I'm going to try to remember and like derive it live, okay? So
okay.
The moment of inertia of a single point mass is mr squared, right? So the mass of the point multiplied by the distance squared. Is that correct? I think so.
Well, it's the sum of all the masses, right? It depends
I'm talking
on the distribution.
I'm talking about one point.
Oh, okay. Then yes.
Mr squared. And so if you have a continuous distribution, you have to take the integral of r squared dm, right? I think that's right. Because you have to multiply the distance r squared times each infinitesimal mass point in the continuous distribution.
Because you're basically integrating it, remember?
Yeah. And so that's how you calculate any distribution. Of course, there are hard distributions to do. For example, the human body would be difficult to integrate over because it's so, it's symmetrical in a way, but just so overly complicated what we did do in class and things like distributions, I really can't talk. Distributions that we did in class that were pretty easy to derive were, for example, spheres, balls that were filled in, you know what I mean? Also planes, like not flying planes, but like two-dimensional flat planes. Also cylinders and things like that. And those are easy, but also interesting to go through, especially the first time you do it, because you'll notice that some axes are easier to do than others. For example, a sphere rotating around just its central axis is different from actually no, this is a bad example because the sphere is completely symmetrical. What about a cylinder? So if you stick the axis through the top of the cylinder, that moment of inertia is going to be different than if you were to like skewer it from the side and it would rotate like a propeller. And so you can do these calculations with the integral that I just mentioned earlier. Some, of course, are easier than others, but they're very interesting because I remember we actually did these derivations before even learning integral calculus, which was which was fun. I remember sitting in my room just saying, okay,
No, but to be honest, come on, these were very easy. These are very easy integrals, though. No, like like the integration itself. Figuring it out is a different thing. That's the whole point of physics.
Yeah,
the integration itself was super simple.
That's what I was talking about, though. Like setting up the integral. Obviously,
yeah, setting up, of course.
It
Okay,
is
that is a little more of physics, in my opinion. Just setting up the whole masses and the understanding like where where it's concentrated and stuff like that. Like that's a little more in the physics terms of it. But I definitely understand. Like that's why it's the classic. You learn more math and physics because you start a lot earlier because it's such a foundational subject. Anyways, we're going crazy. But yeah, super crazy there. What I did want to talk about though was, is it a fair moment to get into torque right now?
Yeah.
Is it a fair moment to get into torque? So torque is super cool because it is the rotational version of force. So again, we're just comparing translation and rotation. So here we have the rotational version of force, which is torque. And it's super cool. And it's basically, the formula for it, this is very, very simple. It's just the radius vector cross the force vector. Super simple. So again, for people who maybe not heard of cross products and stuff like that, it's basically there are two vectors, right? Let me just set up a scenario for you. You have a pivot point.
Isn't it R cross F?
Yeah, that's what I said.
You said that force cross R.
I said that's radius cross. Did I not say radius cross force?
Oh, I thought you said it the other way around.
Well, I'm sorry. I meant radius vector cross force vector, right? Now, for all these scenarios, you need a pivot point. So we have some point, and a pivot point basically means that something is rotating around this point, right? Point of rotation, axis of rotation, whatever. So we have a pivot point, and we have some part where we're applying a force. The easiest scenario to think about, if you aren't able to imagine anything right now, is a door. A simple door, right? Can act exactly like this. So in this scenario, your hinge, where your hinges are, is your pivot point, and where your handle is where you're applying the force. So, I think people can already imagine the scenario. You push it, and it creates some amount of force, and that is what we quantify as torque. And again, the cross product is, again, just a vector product, basically, because at the end of the day, torque is a vector quantity, right? And what all it represents in this case is the amount of, again, you can think about it as rotational force is being applied to said system. And again, you can kind of see something interesting from here, the relationship between the torque and the force and the radius and all this good stuff. Keeping the torque constant, we have F and R basically inversely proportional in a way to think about it. And that is why on every door, you never see your handle at your hinge, right? You see it the farthest away from the hinge because you apply a small force at a great enough distance and you can do anything you want. I brought up a quote because this is a very famous one. Everyone, this is your Archimedes quote. Give me a lever long enough and a fulcrum on which to place it, and I shall move the world. I believe it was him that kind of did this whole. Was it? I'm pretty sure. I mean, how else would he have said it, right? Because he kind of discovered this whole thing where, hey, if I'm far enough, if my radius is long enough, I can just apply a tiny force, and it will relate to a ginormous force on the other side. If the other side radius is very tiny, right? Mm-hmm. Does that make sense? So yeah.
I wanted to say that because torque is a vector quantity, but the magnitude, I guess, quote unquote, the magnitude, because this can also be a negative value. Mm-hmm. Anyways, like the amount of torque that you're applying is force times the radius times sine of the angle between the two.
Yeah, that's the cross product formula, right?
Yeah, but just the number, not the vector.
Yeah.
So what this actually means, and if you think about it for 2 seconds, I feel like that I say that every single
2
episode.
seconds. No one thinks about it in 2 seconds.
If you think about it for 2 seconds, so imagine your door, okay? The vector for the radius goes from the hinge to the handle. If you apply a force in the same direction of that radius vector, you're going to be applying zero torque because your door is not going to be rotating at all. And that's where the sine theta comes in. If your theta is 0, then mathematically you're applying zero torque. And that makes sense because if you're pushing, in the same direction as the door is not going to move. But if you increase the angle at which you're pushing on the door, you'll notice that you're going to get the most torque when you're pushing directly square onto the handle, when you have a 90-degree angle. And then, of course, it decreases until you get to the other side and you're pushing into the hinges, towards the hinges of the door, where you will also have zero torque. And if you know what a sine wave looks like, that's exactly what I just described. So that's how when I get into a problem that has to do with torque and all that, there are 3 things, or maybe 2 things, that I think about. First of all, you need to look at the pivot point, the point of contact, and also the angle of contact. Okay? So the pivot point in this situation would be the hinges. The point of contact is the handle, and then the angle is just at what angle you're putting your arm on the handle. And that's the only information you need to solve any problem. And you can take this idea with the door and apply it to anything that rotates. And that's all the information you ever need. Mm-hmm. There was this difficult problem, or I guess it was difficult at the time, in our physics lab, where we had to describe the motion of a yo-yo, where we put a yo-yo on a table and you rolled up the string, and then what we had to do was pull on the string at different angles and write down what the yo-yo did, and then we had to explain it mathematically. And unexpected things happened, right? You'd pull on the string and the yo-yo would start rolling in the opposite direction. Mm-hmm. The tricky thing about this problem was that I wasn't using my own advice right now, and it's to think about the point of rotation, the point of contact. The point of contact in this situation, because the center of the yo-yo is not a single point, right? The center of the yo-yo is a cylinder, and the string contacts the outside of the cylinder, right, in the center of the yo-yo, which means that from the center of the yo-yo to the point of contact was the radius vector, And then depending on which angle we were holding the string at, right? We did like a horizontal one, we did a vertical one, and also like wrapped around on going the other way, which means that the point of contact was on the top instead of the bottom. We also did a couple of different angles. The point is, the point is, I was expecting it to be super easy. Like, oh, I pull on the string, the yo-yo is just gonna follow, right? But it turns out it was very counterintuitive, and it made me think about these torque problems in a different way. And now I actually think about it for 2 seconds, and it helps me a lot. So, I encourage you to do that too.
Those 2 seconds really help, eh?
For sure.
Those 2 seconds of thought. And again, all where torque plays an important role in just understanding these cool effects. I believe there's a really cool Veritasium video as well that is basically on the axis of rotation. And he does this really cool experiment. You may have seen it in space, where this one thing just forever flips rotations and stuff like that. And that's all because of these crazy torque vectors and just the way they're pointing and stuff like that. Right?
I think that has to do with an unstable equilibrium of the angular momentum vector. And so as soon as it goes off axis,
it switches.
It switches to the other side. Yeah.
Yeah, it's something like that. I don't know if we can go too deep into it because I don't know if we know enough about it to talk about that. That would be definitely a cool thing to know about, though. But anything more on torque that we wanted to talk about?
There are more equations for torque that we didn't talk about. For example, torque equals the moment of inertia multiplied by the angular acceleration of the object. And this is a direct translation from Newton's equations of motion. Remember, force is equal to mass times acceleration. And as we mentioned earlier, mass in the rotational sense is the moment of inertia, and the acceleration is just the angular acceleration. And so having these two equations for torque and being really familiar with them actually helps you a lot, because you have a lot of information, or you can get a lot of possible clues in your questions, and then you just use all of these convenient equations to solve for it. I remember one problem that we had on our second midterm in first year. This was the one with angular rotation and all that stuff. One of the last questions, I don't know if you remember this, Ray, but it was a rotating piece of wood, and on that piece of wood were two like toy cars, and the question was something along the lines of like, what mass do the cars have to be for them to reach the end of the piece of wood in 10 seconds? And the reason why this is difficult is because, they gave us an initial angular velocity for the piece of wood. But of course, as you start rotating the piece of wood, the cars start moving away from the center. And that changes the moment of inertia as a function of time, which changes the angular velocity as a function of time, which has to do with all of this stuff.
I actually do remember a question like that.
Yeah. And I remember just writing down the worst answer of my entire life. And then as soon as the exam was over, I asked one of our friends, and he's like, oh, did you consider like the force of friction? And that was the one thing that I was missing, because I'm pretty sure the force of friction was the force vector that you had to take into consideration for the torque. And I just completely missed that and, butchered the entire question. But I'll try to actually find the question at some point, because I remember I keep my exam booklets, so I'll try to find it and maybe post it on Instagram. Find it at math.physics.podcast.
Ooh, I like that plug. I love that plug. Angular momentum. Yeah, that's a big one. That's a big one. Because we already understand translational momentum, right? Very, very simple, or at least for now, right? Some amount of, okay, well, how do we quantify how tough, how hard this is to stop, or whatever, that's a way of thinking. A moving body is to stop. Angular momentum is, well, very, very, very similar thing in simple terms in the angular sense. But the way it's calculated, quite interesting. So now there's a difference between that small L and the big L, right? Which I always get confused by, because I know the big L is basically just the sum of all the small L's. Again, I know for the people who know the angular momentum equations, you may get what I'm trying to say right now. But basically, a way to think about the angular momentum is the radius, once again, cross the linear momentum. Ooh. So that is basically a formula or a way to think about angular momentum. Understand, again, the same thing with, if you want to make it into a quantifiable, like a number, it's the length of the radius times the magnitude of the momentum multiplied by the angle between those two vectors, right? So it will be at a maximum when it's at a 90 degrees. Angle. Sine of the angle. That's what I meant. Multiplied by the sine of the angle between the two vectors, so it will be maximum again when that angle is 90 degrees, right? And again, you can convert this, because technically momentum you can convert into mv. You can take out mv is your vector, and then you have your p, your r cross v basically is what you have. So that's another way of thinking about it, that your linear momentum is now directly related to your radius or the multiplication or the of the radius and the velocity, basically, right? So again, if you just break it down into the numbers, because it's basically just m you take out, again, forget the mass for now, we have your r, v, sine theta. So again, it's mainly your relationship between r and v, and that you can break up into r cross v, taking m out of the picture. So again, another way to think about angular momentum in terms of our linear counterparts, but again, just understanding it. Again, why is it important? I don't think it really needs to be asked at this point. But again, it's a way to quantify that number, right? It's a way to quantify the amount. Now, that capital L, small l, all that stuff that I was just talking about, for people that maybe have not heard of angular momentum before, what I was just describing to you, this r cross p, because p is momentum, is the small l. Again, that's just, I guess, the variable that we define it as. And this is basically, because remember, in any system, there can be multiple different masses moving at different momentums, whatever. So your angular momentum of the system is basically the sum of all these small L's. Very simple. Basically the sum of all of these small guys. So I guess if there's only one thing that's happening, and they're not multiple masses, multiple momentums that are moving, then you can just use this one equation. Simple, done. Just that small L equation. And another way to think about this, if you want it in strictly angular terms, is the moment of inertia multiplied by the angular velocity of said body. And again, if you want to think about it, again, I believe I brought this up. Mass and moment of inertia directly related. Velocity, angular velocity, directly related. So P equals mv, which is linear, is directly translated to angular momentum equals I omega. Right? So just again, just understanding those relationships. And angular momentum becomes very important, especially because we were talking about torque.
Mm-hmm.
Right?
As you know,
yeah,
as every single person on Earth knows.
Oh my. Please don't put this pressure on
the force is a calculation, as one might say, of the change of momentum.
There's no way everyone knows that. This guy.
I was kidding.
No, I feel it.
But it's a fact.
Yeah,
okay?
Yeah.
So think about an object that's moving in a straight line in space, and it's just chilling. For anything to happen to that object, there needs to be a force. And what does that force do? Well, it changes its momentum, and the amount by which the momentum changes is exactly the force. So if you want to stop an object, you need to apply a force that goes against the momentum vector until the momentum vector equals 0. And that is the force that you applied. Boom. Okay?
Mm-hmm.
Now, as we've been saying this entire time, that the translational equations go directly into rotational equations via changing a couple of variables, changing position for angle, angular velocity for regular velocity, all these things. We know that force is the time derivative of momentum. We know that momentum has a direct counterpart and is angular momentum. Therefore, I've constructed the perfect bulletproof argument to explain that torque is equal to the time derivative of angular momentum.
Mm-hmm. Exactly.
So now we have 3 equations. We have 3 equations for torque. We have dl dt, we have I alpha, and we also have r cross f.
Wow.
Anything to add, Ray?
I don't think we have any. I mean, with the formulas, with the formulas, I think that's all the formulas we know of currently. When it comes with the torque, I was just thinking of adding. I guess not really, because when it comes to all of this, right? It's also important to remember that these are all vector quantities, so you have to preserve that. Now, if people kind of picked up on the whole R cross F, R cross P situation, then people are also aware that both R, F, and P lie on the plane of rotation, right? So wherever this body is rotating, take the door, for example, that's the plane of rotation, right? So we have the force acting on that plane, we have the radius on that plane, and now, because again, that's a 2D plane, right? And the torque, again, R cross F, is perpendicular to that plane. So it's basically pointing up. It's pointing outside. Again, I'm saying up because I'm just imagining it like on the floor. And I'm just thinking about like me pushing a wheel around, like around a pivot point. So the torque would be pointing upwards because, again, it's R cross off F.
So the right-hand rule.
The right-hand rule. This is the right-hand. I mean, I think that was, okay, I don't know if people, this is mainly got from cross products. But it's basically the right-hand rule, very straightforward. Put your, oh, wait, I was doing something complete. I guess that's also valid, though. I was doing the grip rule, like where you curl. I guess that also works. No, it's the same thing. It's the same thing. So basically, you point your 4 fingers in the direction of the first vector, and then you curl in the direction of the second vector. Or you can just point 2 fingers or whatever. And the reason and the way to do that, and the reason it's important is because, and this is only using your right hand, the direction that your thumb is pointing in is the direction of said vector. So in this case, if you have, again, just imagine, I'm just like imagining a door, and I'm imagining like a top-down view. You know how you're pushing a door? Imagine like a top-down view of that door. And if you have your radius, so you're pointing outside, and then if, let's say, you're pushing forward, you're curling your fingers on top. So you have that vector pointing straight upwards towards yourself, right? So again, all this to basically say angular momentum and torque also point in the same direction, right? They point both perpendicular to the plane of rotation. Now,
that's not, wait, hold on.
Wait.
Angular momentum and torque.
They point perpendicular to the... Yeah, they point perpendicular to the plane of rotation, though, not necessarily in the same direction.
To each other.
Yeah, not necessarily in the same direction. Sorry, what I meant was that they point perpendicular to the plane of rotation, is what I meant to say. Now, the reason this is important is because of really cool properties of these guys pointing not towards the plane. And with that, we get things like gyroscopes and precession. And like the Earth wobbling every few centuries. All that good stuff happens because of the simple reason of this thing rotating around and because of these vectors all pulling and pushing each other in one particular direction, right? So I don't know. I just wanted to bring up now. I'm gonna be completely honest. I did want to do a whole thing on gyroscopes, but I couldn't find, like, in my opinion, I couldn't find a deep enough explanation for me to really go off on it. So I'm just gonna explain it.
I want to do it.
You want to go off on gyroscopes?
No.
Go for it.
No, gyroscopes are awesome.
I just wanted to introduce the whole idea, because I just wanted to introduce gyroscopes in the sense that if you haven't heard of it, it's basically a navigation tool. Because the best thing about it is no matter how much you move it, it will be pointing, or the axis of rotation will be pointing in the same direction, wherever you move it in space. And it works through a very simple principle of conservation of angular momentum. Right? I mean, if you want to go off on it, I'll let you go off on it.
Yeah. Okay. So, I like to think about the gyroscope that you can buy like at a museum or whatever. The one where there's like a metal rod, I guess, and in the middle of the rod there's the rotating wheel. Like
the bicycle thing is what you're thinking? I think that's the most common one, right?
Yeah, kind of
like the bicycle.
That, yeah.
Like the bicycle.
Yeah.
I mean, this is a very common one. Again, a bicycle attached to the string.
Yeah.
So there's a rod,
yeah.
Bicycle in the middle, string is attached, and somehow.
But I'm talking about, the small one, like the small metal one that
you're talking about this. Oh, you're talking. Okay. That's a little. Okay, I'm just talking about like the one that people are. Because I don't know, when I think of a gyroscope, that's the first thing I see. That bicycle wheel, that huge bicycle wheel. I don't know. Maybe it's because I've just seen a lot of videos like that. So, anyways, a quick search for a gyroscope on Google will get you a good explanation of what both of us are talking about. But yeah, continue.
So boom, when you start spinning the wheel, okay, the wheel is horizontal. You start spinning the wheel, you give that wheel an angular momentum. And if that wheel is spinning counterclockwise, the angular momentum vector, using the right hand rule, will point upwards. Okay? And as we said a little bit earlier, torque is the time derivative of the angular momentum. Now keep that in mind, okay? So when you put the gyroscope on your finger or whatever, you're probably amazed at how it stays up. You're like, wow, this piece of metal is balancing on my finger. It looks like magic, okay? But in fact, think about what I just said about the time derivative of angular momentum. So you need to actually, in order to change the angular momentum vector, you need to apply torque, okay? That's why they're equivalents, which means that you need some kind of force, because torque requires a force and a distance from the point of rotation. Now, in this case, the point of rotation is your finger, because that's what the gyroscope is balancing on. Mm-hmm. So if the gyroscope were to fall off of your finger, it would be rotating around your finger. And the force, you could probably guess in this case, is the force of gravity, which points downwards. Okay? Mm-hmm. And so, at first, this is why as soon as you start your gyroscope, it's spinning very quickly. You put it on your finger, and it seems to be perfectly stable. It is perfectly stable because, as you remember, R cross F, there's the sine theta term. The R vector points upwards in general, and the F vector points downwards, which means that the angle between them is 180 degrees, or pi radian. And the sine of pi is 0. So at first, there is 0 torque acting on your gyroscope, and it is perfectly sitting still on your finger. But as friction occurs, and natural human error and things like that, the angular momentum vector starts to decrease because the wheel starts slowing down. And also, you move your finger around, you start to knock the gyroscope off of its balance point and all that stuff. Now, the more the gyroscope starts to angle downwards, the more the sine theta term becomes positive, or I guess the the absolute value of the sine theta term increases. Okay, and so once again, let's use the right hand rule. The r term is going to be pointing off in the angle of the gyroscope as it starts to angle downwards, and the force term is always pointing downwards. Okay, so if we do the cross product, r cross f, as that angle increases, you see that your thumb actually points sideways. And that's what causes the gyroscope to precess, to do circles, because you have an angular momentum vector from the wheel, and that vector starts pointing upwards, and it starts to go down as your gyroscope starts angling downwards. But the more it angles downwards, the higher the torque starts to push it sideways. And so that's why it doesn't just immediately fall off of your finger, is because the gravity that is pulling, translationally, it's pulling your gyroscope downwards, but that very force is what is driving it to continue to precess and to move around your finger in a rotating fashion. And as you know, when the r vector and the f vector are perfectly perpendicular, so that means when the gyroscope is perfectly sideways, that's when the torque is the highest. And so it slowly starts to precess, and then as it keeps falling down, it'll keep going faster and faster until the wheel just stops.
Basically,
and then falls.
the closer it is the falling, the more it is to come back, which is why it's perfect. Like kind of, you know what I mean? When it's at the peak, it starts to come back. You know what I mean? It's coming, like it's decelerating almost, and then it's accelerating. Like, I don't know, like a way to think about it. I know that's not exact at all really what's happening, but and another consequence of this, right? As you were talking about precession, is with this. Well, there's also wobbling that then is also caused with all this stuff. But just dealing in space, in Earth here for now, air friction doesn't always last forever, right? So that precession that you see, that going around and round and round, that you see that spinning top also follow, will one day come to a standstill simply because of air friction. So if we were in space, that would just keep on going on, right? So again, I wanted to bring in gyroscopes. Really dope explanation. Again, good explanation. I just want to say that because nice way to think about it. I think I really wanted to end with the gyroscope because I know rotational motion is really cool. It's really important, but it's not really that cool until you see some interesting applications, and the gyroscope is one of the coolest, in my opinion, applications of rotational motion, right? Because it can be used everywhere for everything. I believe it was used in missiles in in all these wars. Not that that's a good thing to use it for, but in all rocketry, of course. It's again just to measure, keep direction very, very, very precisely, because the whole point of this again. So the beauty again isn't the fact that it continues. Well, that is kind of cool that it just continues going on around that finger of yours. But the beauty is...
no, that's only a consequence of it slowing down. But if it continues to spin like they do in navigational systems and all that stuff, that's why, it'll just stay in the same place.
That's exactly what I'm saying, right? So that's that axis of rotation is what the beauty is, where the beauty really lies, and the fact that is not changing is real. So the classic thing that, again, I'm thinking of, again, a lot of our listeners may have heard of Walter Lewin. Very, very, very popular. You know that physics professor, that crazy guy. I know you know him, but a lot of our listeners definitely also know him. And again, that's that classic gyroscope example where you spin that bike wheel and you put it on that's just the one I was thinking about. So when you said finger, I just got a little bit. But yeah, and it's really cool to look at, hey, how is that somehow defying gravity, right? Because it's just spinning around. But that's not even the cool thing. The cool thing is that axis is staying in the same direction no matter where we move it, right? And that's used for all types of gimbals today. That's how gimbals work in the first place. So all of that is dependent on just simple rotational motion. Yeah.
Awesome. Well, thank you very much to everybody for having listened to this episode.
Yep.
If you like this episode, make sure to leave a like. Make sure to review us. Leave a 5-star wherever you're listening to this podcast.
Yeah.
Make sure to follow us and to share us. Also, let us know what you want us to talk about. We'll talk about pretty much anything, I guess. You can hit us up on Instagram at math.physics.podcast. Also, you can send us an email, math.physics.podcast@gmail.com.
Yep.
And thank you very much, everybody. This has been episode number 74. I am your host, Parker.
And I'm Ray. And we will see you soon.
Bye, guys.